Hi, third graders. Today we're going to review how to multiply using arrays and tape diagrams. The first thing I want to remind you is vocabulary for multiplication. Remember, the two smaller numbers that we're multiplying are called factors, and the answer to a multiplication problem is called a product. So remember, it's factor times factor equals product. Also, remember, pictures that we'll be using today are arrays and tape diagrams. Let's start with the first problem. I'm going to pick two factors for my multiplication problem. Let's go with 3 times 7, and the product is what we're trying to find. So factor, factor, and the missing number is the product. We'll start out using an array to solve this problem first, but before we do, I want to remind you, if you know that 3 times 7 is 21, just write 21. You don't have to use these strategies to write the answer unless you're trying to prove your answer, or unless you're required to use a picture to prove it, or a picture to solve it. But let's use that array first. So we're going to start with the first number, 3. Remember, it means 3 groups of something. So we're going to start with 3 groups of 7. So if we're going to use an array for 3 times 7, we're going to start with group 1, group 2, and group 3. So because we need 3 groups of 7 or 3 rows of 7, we're going to say 1, remember that one counts, 1, 2, 3, 4, 5, 6, and 7. There's group 1. We already have 1, so say 1, 2, 3, 4, 5, 6, and 7. We have 2 groups of 7, but we need 3 groups of 7. 1, 2, 3, 4, 5, 6, and 7. What we have here are 3 groups of 7. You'll see the groups. There's group 1, there's group 2, and there's group 3. Now to find 3 times 7, there's a few ways you can do this. You can count each one, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 21. Or if you're good at skip counting, if you know that 7 and 7 is 14, you could just say I have 14 and then go 15, 16, 17, 18, 19, 20, 21. So 7, 7, and 7, 3 sevens is 21. So the answer to our multiplication problem is proven by our array is 21. But we also want to remember that we could do this using the commutative property. And the commutative property says that we can switch these factors around and we'll still get the product. For example, instead of 3 groups of 7, we could do, if you said 7 groups of 3, you were right. That's a commutative property. So instead of doing 3 groups of 7, I could do 7 groups of 3. And remember, we can model that by just turning our page this way. And here we have 1 group of 3, 2 groups of 3, 3 groups of 3, 4 groups of 3, 5 groups, 6 groups, and 7 groups. And 7 groups of 3 is indeed 21. The next thing we need to be able to do is use a tape diagram to solve our problem. So we'll go ahead and start with 3 groups of 7. Once again, I'll draw my tape diagram. Okay, I'm going to ask you a question. Be ready. I know I need 3 groups in my tape diagram. So if I need 3 groups, how many lines do I draw? If you said 2, you were right. 1, 2. 2 lines will give me 3 parts of my tape diagram. Each part of this tape diagram is called a unit. So this is 1, 2, and 3. I have 3 individual units because I have 3 groups, and I know that I need 7 in each group. A couple ways you can do this one. You can just write 7 inside each one. That works really well if you know how to count by 7, 7, 14, 21. If you're not so good at counting by 7s, you could always use place value discs. So you could actually draw 7 place value discs instead, and then you could count them up. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. And you could do the same thing here. And then you could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, on over to 21. So altogether, 3 groups of 7. Our total then, part, and our total would be 21. Once again, that commutative property hops in there, so feel free to do that as well. Instead of 3 groups of 7, you can turn those factors around and get 7 groups of 3. If you wanted to model that one, you would draw another tape diagram. Only this time, instead of 3 parts, remember we're going to turn it around, which means we're going to have 7 parts with 3 in each part. Question for you, if I need 7 parts in my tape diagram, 7 parts, how many lines do I draw? Did you say 6? 1, 2, 3, 4, 5, and 6. If I draw 6 lines, I get 7 parts. And inside of each part, I'm going to put 3. Once again, I can use the number 3, or I could use 3 place value discs in each one. This time I'm going to do a little bit different. This time I'm going to skip count as I go. So I'm going to put 3 here, and since I know this is going to have 3 more, I'm going to go 3, 6. I'm really good at counting by 3s. That's why I'm doing it this way. 3, this would give me 6, this would give me 9, this would give me 12, 15, 18, and 21. What I'm really doing is putting 3 in each unit, but just to save myself some time, I would skip counting by 3, so then when I get to the end, I know my grand total is 21. So I now know 3 times 7 is 21. I also know 7 times 3 is 21. And that is how we can use arrays and tape diagrams to either prove our answer or to solve our equation. That's it for today.